So my name is George Stein, and I'm a postdoc at Berkeley. And I've been working on a variety of machine learning things for cosmology lately. But one of them that I'm very excited about is self-supervised representation learning. And this is something that's really, exploded in the last few years in computer vision and natural language processing. If you've been to any of these machine learning conferences, you've probably heard a lot about self-supervised representation learning. But we've been working on applying it to specifically galaxy surveys. So first off, we're going to need in the future, when we don't have many labels or when we just have these excessively large data sets, you're going to need techniques that can learn without labeled data. So self-supervised learning is one of these, where what you're doing is you're trying to obtain supervisory signals from the data itself. And you're trying to create some mapping from your data to some low dimensional representation that ideally contains all the information of your data, minus all the noise and instrumental effects. So there's been a number of methods proposed, even in this workshop, on how to extract features or representations from your data. These are things like just, pre-trained networks, pass your data through a pre-trained network, get out some representation and do whatever you want with that. These are preset kernels like the scattering transform, tsne, umap, train an autoencoder. So there's all these variety of methods to go from data to low dimensional representation. But what you find, I'll use this imaging example on the right here. What you find is that small perturbations and symmetries in this data set can massively affect the representation that comes out. So if you look at those two galaxies, you can take one galaxy, copy it over. You can rotate these things, you can add noise, you can mask bits, you can jitter it. You can do all these realistic effects that happen in real data. And if you pass these through some of these feature learning techniques that I mentioned, what you'll find is that even though by eye you can tell it's the same image, sure, the pixel values have changed, but what's physically represented there is the same thing. What you'll find is that the features that come out of your network are completely different. This image just pinballs down in two separate ways. And even though it's the same physical object, you want to infer the same physical properties, you get completely different representations. So self-supervised learning is trying to improve on this. We're trying to learn representations that are invariant to any complex instrumental noise you want to throw at it, observational effects, and data symmetries, rotations, jitters, crops, all of these things. So on the right, this is one way to do it, which we used in our initial work on this, which is momentum contrastive learning. So what you're doing here is you're taking the way you're learning representations, rather than just compressing data, is you're taking, say, an image, and you're making two views of this image, two augmentations, where both of them are just, you throw instrumental noise at it, observational effects, you're rotating it across all the symmetries that you have, and you're passing this through your encoder, through just a CNN, ResNet 50, and whatever you like. And the goal here is to make the two representations that come out of these two heads of the network, the goal is to make these the same representation or as similar as possible while making it different from all other representations. So you're explicitly training your network where even though it's rotated, it's noisy, whatever you threw at it to look different, you're telling it that no, that is the same physical object. So learn the same physical representation. So if you go to the next slide, what we can do with that is a lot of things, because this isn't a specific architecture. This is just a technique to pre-train your network. So you use your entire data set, don't need any labels, and you just train your network to group together similar images and push away images that are not similar to make this representational feature vector. And here are three applications that we've applied this to good results, at least in our opinion. So we've tried doing photometric redshift prediction. So that's what I'm showing on the left here, where you're seeing the amount of labeled data on the x-axis and the dispersion of the redshift prediction on the y-axis. And you're finding that with the same amount of data, you can improve your predictions just by doing this self-supervised learning first. Or equivalently, you're multiplying the amount of data you have by some factor, equivalently multiplying it by a factor of 2 to a factor of 16, depending on the application. So that's one application where we're finding we're beating supervised learning there. Another thing is just, what do you do when you have minimal labels? So in this middle panel here, 256 labels, you're obviously going to struggle to train a ResNet with 20 million parameters. But since you've already pre-trained this thing using contrastive self-supervised learning, we find that we can get pretty accurate predictions on galaxy morphologies, is this example. And additionally, it allows some very powerful tools for data discovery, data organization, and anomaly detection, which I'm showing on the right here. This is if you click on that link, this is an interactive app that we created where you can do sort of like a Google image search. Paste your favorite galaxy from the DESI legacy imaging and find every other galaxy in the data set that looks similar. So that might be my 5 minutes, over my 5 minutes, sorry. So that's one of the methods that we think is very useful in cosmological applications, and I'd love to talk to anybody about it on Slack or email or whatever you want.
Okay, thanks. We'll take any questions. Okay, yeah, feel free to email him or on Slack. Okay, so next up.
Sounds good. Thanks, everyone.
Thanks. So next up we have Hongqin Chen. And this is a challenge. So remember, so the challenges are kind of problems you think we could solve with ML, and you want to kind of pitch it, and maybe you could work on it at the half day.
Okay. Hi, I'm Hongqin Chen from University of Chicago. I mostly work on simulating the cosmic reionization, especially the quasar approximatisms. And today I'd like to talk about challenge in the field of reionization, that is, which is to how to accurately predict the quasar continuum. This is relevant to a lot of topics of reionization, for example, measuring the Gunn-Peterson optical depth and recover the density field. So in our recent paper published this year, we find that the density field at redshift 6 can be recovered in the quasar approximatisms. And using this recovered density field, we can learn a lot about the large-scale structure at redshift 6, as well as the environment and the growth of the first quasars. And with this method, we also want to apply it to observational data. So me and our collaboration, the XQR30 team, is actively working on applying this method to a set of a new high-resolution reionization epoch quasar spectra. So here is one example. So the region in this red box is the quasar approximatisms, and you can see a lot of absorption features, and these are mostly caused by the denser gas, mostly in filaments, just like in the low redshift Lyman alpha forest. So when after we measure the optical depth of each pixel, we compare it with a baseline model, and then we can recover the density field shown as the black lines in this lower panel. So after we have a sample of quasars, then we can build some statistics. For example, we can measure the cumulative distribution function of the gas, of the density of the gas. And then, so this blue band in this middle panel is the measurement from 5 of our quasar sign lines. And with this, we can potentially use to constraint the cosmology, like the constraint sigma 8. And this measurement, this new measurement at redshift 6 opens a new window for us to understand the cosmology. And we can see that with only 5 quasar sign we can already potentially constrain the sigma 8 to 10% level. But one major systematics that this kind of analyze and many of the reionization analyze will encounter is the quasar continuum. How do we know if we estimate the continuum accurately enough in this blue side? Because at redshift 6, there are too much residual neutral hydrogen, and this blue side is heavily absorbed, not like the lower redshift, where the blue side is pretty, it's much easier to reconstruct. Can you go to the next one? So the way that we usually construct the blue side of the continuum is to learn from a sample of lower redshift quasars and build in a method to extract the information from the red side to predict the blue side continuum. So usually the commonly used methods are for example, the PCA based, basically choose a set of principal components and then represent every quasar with a bunch of weights in both the red side and blue side, and then find a way to map the red side weights to the blue sides. And in the classical PCA, we just need to try to find the best matrix that do a linear mapping. And in the first panel there shows the bias and the uncertainty in this kind of classical PCA method. And later there are improvements, like instead of using a linear mapping, we use a neural network. So the second panel shows like replacing this linear mapping with a fully connected neural network, how this prediction can improve. And also there are more other methods coming, like the nearest neighbor or deep learning machinery. So it's promising to see that bias can be lower to like much less than 10%. But one big complication for this, the whole quasar spectral analysis, is that how do we know that the machine trained at the lower redshift also work well in the higher redshift? So there are a lot of observational evidence showing that higher redshift quasars show a quite different features. For example, many of the high redshift quasars has a blue shifted carbon 4 emission lines, and it's important to like really find the representative sample to train at the lower redshift. And also, how should we build up like how do we measure the performance of this method at a higher redshift? And also, there are a lot of systematic differences in the data quality at higher redshift. So I myself didn't involve in this this problem. So most of these results are from my collaborator, Sarah Bosman. And so I just want to show this challenge here and to see if the experts here have any thoughts. And also, so I'm currently thinking about like probably add the recovered density field as the additional information to somehow collectively fit the data, or so to test this, both the fitting and the continuum estimate how well the continuum fitting is, and that's it.
Okay, thanks. Any questions? I have one. So the nearest neighbor averaging, is there any problem, like, because you're averaging quasars with the most similar features, is there any problem caused by like the quasar being too smooth, like the continuum being too smooth? Like, do you want to reproduce the higher frequency features?
No, I mean there shouldn't be any high frequency feature because we are the continuum is quite smooth. Yeah.
Okay. Cool. Okay. Any other questions? Yes.
Wouldn't self-organizing map be great for that? And then you can cluster. You can also add a cluster thing on top, so you can do something similar to the nearest neighbor, I guess. But then the self-organizing map, like, kind of learns the features. Yeah, I don't know.
I'm not very familiar, but I'd like to chat more about.
Yeah, maybe it's maybe PCA is enough, but yeah, happy to talk about it. Yeah.
Great, thank you. Shihao Chen, you wanna?
Actually, I updated the slide.
Would it be possible to refresh the Google Slides? Who's controlling it? Whoever's controlling the slides.
Well, maybe it's on this.
No, it's not on this computer. Oh, there we go.
No, sorry. I mean,
Sorry?
quit and display again.
Oh.
Just make it basically more
Yeah, I don't know who's controlling it.
Would it be possible to refresh
Where's the room?
this particular slide?
Oh yeah, can we refresh it? Okay, thanks.
Yeah, so I didn't realize that this is a new representation, presentation. So I mean, there are some overlapping from yesterday, but I tried to make bigger picture claims here, and avoid the details I presented yesterday. So the challenge I think here we have is how to extract information from field, right? And especially because the field are complicated high-dimensional objects. So one main point I want to argue is that the method should basically match the property of the data, especially complexity level. This is kind of the same thing as there's no free lunch, right? So you have the set of data. Now we have data to learn, but the problem is you have this limited, finite set of data, and the more prior knowledge inject in this learning process, the more meaningful information you can learn. So if you just have a very flexible neural net and let it to learn from a finite data set, so usually what they learn, most of the results will not be really meaningful, will be what we've already learned, known. So the idea is still that for not very complicated data set, we want to inject as much as possible known knowledge, like including the invariance we talked about. And one other knowledge, I think, it's about the information as a function of scales. So I'll not go through details, but I think that's basically why the scattering transform and the hierarchical convolution architecture in convolutional neural net works so well. Right, so here the idea is that, again, repeating myself, most of the physical fields I think we encounter are not as complicated as the biological world. So really, we don't need to learn new vocabularies from data. We just need to use some very generic vocabularies to describe the field. It's just that in the past, we didn't find the correct vocabulary to do that. So I think now people have a tendency that, like in the past, we have the power spectrum basically alone. And now we have CNN, and people have a tendency that as long as the field is not describable by a power spectrum, we just suddenly jump to the CNN. But actually, I think that the level of complexity of them are very different. And for most physical fields, perhaps something in between, still with generic vocabulary instead of learning things, are very valuable still. And as I said yesterday, the scattering transform is one of these choices. And again, here I want to emphasize the properties of the main advantage of scattering transform, which is actually it's easy to use. So again, an advertisement here. Basically, anywhere you can use power spectrum, you can try the scattering transform. For example, the turbulence field and the cosmic density field. And almost everywhere you tend to use CNN nowadays, you can step back a bit and be more conservative and try the scattering transform. And we constantly find that they will give you very similar results. I'll show something like in the next slide. And again, the third property is it has its built-in invariance and it's interpretable. So the next slide, yeah, I think what George mentioned is it's very nice, which is these problems are actually about reducing the dimensionality of the high dimension object of a field. So and the scattering transform provides you such a representation. And this representation can be used in all different applications, including data exploration when you don't have model, and classification when you have discrete model, or parameter regression when you have parameterized continuous model. So here I'm showing one example of data exploration. It's about the ocean temperature field, which reflects the turbulence property. And what the state of art, again, now, of course, is about using CNN. So the problem here is to try to find outliers. And CNN basically finds the upper part of what I've got here. This arrangement is the S2 and coefficient I introduced yesterday. But one thing we realize is that if you just calculate second coefficient and you pick the upper part, which are very extreme examples, they basically match what CNN finds for you. And what's interesting that there are also other corner of these scatter plots, right? And there are also extreme things, but the CNN kind of just ignores that because in a field, right, you have extremely large values, but you also have extremely quite small values. But CNN, just because of distribution here, there's a long tail in the large values. So CNN tends to think those large value fields are extreme. But there are also some very interesting, like the edges, which are very rare in this data set and located in one particular position on the Earth, but CNN just ignore that. So I think here is why such a, I mean, generic vocabulary sometimes can do better than CNN. And yeah, I'll stop here. And really encourage you to try the scattering transform in your field. Thank you.
Thanks. Does anyone have any questions for Sihao?
I have one question. Is there any like equivalent to a scattering transform on a graph? Because I really like using like graph networks in deep sets because like astrophysics is like there's like a lot of empty space. Is there anything like a scattering transform for a graph?
Yeah, I think the answer is yes. I'm not very familiar with that, but I think in 2018 there's a paper about the scattering transform to graph. They extend the kind of invariance scattering idea to graph, and yeah.
Thanks.
Also, please, I'm talking to the people on Zoom. Please feel free to ask questions in the chat. I have the chat window open now. So, any other questions? If not, let's move on to the next.
Okay. So I just wanted to mention my software called Pyser. So if you're interested in doing what's called symbolic regression, it's a very interpretable way of doing machine learning. It does a search for equations for a given data set. I encourage you to check out this software on GitHub. It's all Python, so you can kind of plug it into your pipeline. It's also really useful for like interpreting a neural network. Can you go to the next slide? So as an example, it's a bit blurry, but basically, like if you have a data set, you have like 100 rows, 5 features, you could kind of you could write out like a test equation. So this is 2 times cosine x3 plus x0 squared minus 2. You give it to Pyser. You declare like Pyser is allowed to use plus, multiplication, and cosine exponent sign. So those are like the operators it can use. And at the end, this only takes like 5 minutes for this example, and it finds the correct equation. And so we have like this one example paper where we rediscovered like m times m2 over r squared from solar system data, which is pretty interesting. And it's this example we also found the planetary masses like and the law at the same time. Which was that was a really fun project. Yeah, I'm happy to take questions on this.
Okay, but I have a question. In this application, like, does this work well even for like noisy data?
For noise, it does tend to overfit. So what you do, you kind of you tune the trade-off between the accuracy of your equation and the complexity of the equation. So there's a curve. It's called the Pareto curve. That it's a curve from like if you imagine mean squared error on the y-axis, complexity on the x-axis. You keep increasing the complexity of the equation, you're going to get better results. So you pick somewhere in the middle.
So then, like
for maybe like heteroscedastic noise or like any noise that's kind of variable, that you can put in weights. So you could use like 1 over sigma squared as the weight.
I see.
And then it would, and you can also define like a custom loss. You can write a function as a loss. So you can define like custom likelihoods if you want.
And you can control the complexity by just specifying what functions.
So it'll return like this is the best equation at this complexity. And the complexity is really simple. It's just the number of tokens in the equation. So like every operator is a token, every variable is a token. So it just counts the number of things in the equation, basically. Yeah.
So, but the complexity you want is something that you set, or does it do?
So complexity is set to 1 for every equation. I'm thinking of like adding this eventually. You could define it like as per operator complexity. But right now it's just every operator is 1 complexity.
Okay.
It just counts the number of operators in the equation. I mean,
Okay.
it's like completely meaningless, but it is a way of defining complexity in the equation.
Okay. So you just have to set the operators, but you still have to have a good guess of what you expect, no? Like.
I mean, like a lot of astrophysical equations, you can get away with just like plus, multiplication, subtraction, division, and maybe like exponent.
Mm-hmm.
You can get like many astrophysical equations.
Okay.
So you don't really need to have a prior on your equation, really. Yeah.
Cool.
Yeah.
So I have been using it. It's of course amazing. So I wanted to ask you your advice. So sometimes when you don't find like a good equation, I mean, what do? You put more operators, or you clean the data? Or...
Yeah, I think so. So there's like this internal like denoising. So you can put like denoise equals true as an argument, and it'll clean the data with the Gaussian process and kind of return the average function of the Gaussian process, and that's much better to fit to than like noisy data. And you can also resample it. So if your data is kind of skewed, maybe you only have like a lot of low mass objects and you want to fit at higher masses too, you can use the Gaussian process feature to kind of like resample it on an even grid, and then you can get better equations that way. I think we're almost, okay, yeah.
So when you set a complexity, does it always return an equation with that complexity, or can it return
So
with
you
lower
set max complexity, it'll
max.
return an equation at every complexity.
at every? Okay.
Yeah. And the more complex, the better accuracy. Yeah.
So when you say complexity, the number of terms.
Yep.
Does this code know how to do compound equations? Like substitute an equation inside an equation.
No.
Okay.
So I'll talk about this later today. But you basically like you want to split it up into separate equations.
Yeah.
It can't really learn like a hierarchical thing.
Oh, thanks.
Okay, thanks.
Thank you. Next we have Siema. Is that remote? Or no? Remote?
Siemac, are you online?
I don't think so. So we'll,
If not, we could.
yeah, we can go
come
back to it. Yeah. All right, Brian.
Oh, hi. Can you hear me?
Great. Yes.
So I would like to take this time to share with you my recent work with Zoltan. So from Columbia, and you can check my email there. So in this work, we're investigating the problem of constraining cosmology with baryonic effects by neural networks from reclancing maps. So first of all, I want to point out to you that there are at least two challenges in getting small-scale information from reclancing maps. So the first one is, of course, the information is non-Gaussian. So in this work, we take neural networks as our subjects and see how they perform in their specific task. And the second one is baryonic effects. We think baryonic effects are really important here because we know it affects reclaimed signal, but we don't know exactly how and by how much. So our approach in this work is to employ the baryonic correction model proposed in the RICO 2020. So how it works is it takes dark matter halos from n-body simulations and replace the halo particles by a profile that with baryons. So instead of only dark matter, there are 4 components: dark matter and 3 baryons: Ag and feedback, bounded gas, and stars. And the profile and weight of these components are controlled by 4 baryonic parameters. So the idea of this baryonic correction model is that we are not committing ourselves to only one baryonic model, as is done in many hydro simulations, but we can test against a variety of baryonic physics. The difference that it brings is when doing parameter inference, instead of doing just cosmological, for example, omega m sigma 8, we need to constrain 4 additional baryonic parameters. And when we want to know the constraints on omega m sigma 8, we need to marginalize over baryonic parameters. The network we use is an architecture similar to ResNet. So we take a 500 by 500 map, downscale it, and go through residual blocks, and finally gives out like 6 numbers. So here I show you some preliminary results. We check the omega m sigma 8, 1 sigma credible contour area in an HSC-like survey. Of course, all of these are from simulations. So there are 2 scenarios. The first one is fixed baryons, which means we have a fixed set of baryonic parameters to be taken to their fiducial values and check the area. And the second one is marginalized over baryons. So we can divide these 2 numbers to get marginalized divided by fixed. So that number shows you how much degradation do we expect due to the uncertainty of baryonic physics. And there are 3 methods, power spectrum, neural network, and these 2 combined. So there are 2 conclusions. The first one is, if you check the red numbers, even when we marginalize over baryonic parameters, the neural network still performs substantially better than power spectrum. So it's not as good as by a factor of 2, like for fixed baryons. It is found by many previous studies, but still better, like 30% better. And second conclusion is when we check the green number, the marginalized over fixed ratio is only 2.48 for the 2 methods combined. So this number is lower than either of these 2, which means the degeneracy between cosmological and baryonic parameters are different for power spectrum and neural network. So when we combine these 2, we can get better constraints in both cosmological space and baryonic space. We are still looking for a full explanation for that, but that's all I would like to share with you for now.
Thanks, Brian. Does anyone have any questions for Brian? Paco?
So very nice work, Brian. So maybe I didn't understand. So combine, you mean power spectrum plus CNN?
Yes, we just take power spectrum as a few numbers, few observables, and the predictions by CNN on the map as 6 observables, and just put them together and do a constraint and run an MCMC.
And do you understand why the combine is doing better than the CNN? I mean,
so one explanation that I showed you, there are certain degeneracies between the constraint on cosmological and baryonic parameters. If that kind of degeneracy is different between these 2 methods, when we combine these 2, we can get a better constraint.
All right, thanks, Brian. Due to the interest of time, we're going to have to move on to the next pitch.
Mm-hmm.
Xiaohan?
Hi. Yeah, so this is something I've been thinking about for a while, but I'm not really sure whether this can really be done in like 5 or 10 years' time. So the motivation is really simple. I used to work on cosmological simulations of galaxy formation. And when you look at galaxies in these simulations, you're not really looking at galaxies, you're looking at just mosaics. So how do we describe what's below the resolution limits? So I want to just bring up this work by Michael Brenner's group at Harvard. So this guy is from applied math, not astronomy. But what they did is like they trained a neural net to describe what's happening at the subgrid level. So let's just consider like solving a simple 1D fluid equation. And the velocity here, the time derivative of the velocity is a function of like say time position, the derivative, and the second derivative, etc. So in the simplest case, we can substitute the first derivative using the finite difference method. And then if you want to do like more complicated or more accurate methods, you can do like a polynomial to substitute the derivative with respect to the position. And then in the end, you might just end up solving like the equation here. So in the simplest case, you would just substitute every derivative with like a polynomial in velocity. And so, but in this case, you're actually losing information at a subgrid level by doing this finite difference. So what Michael did with his students is that they trained a neural net by using like simulations with various resolutions. So they go just like finer and finer resolution, and they trained a neural net to substitute the right-hand side of the equation. So they're just not just using the finite difference, but they're using predictions from the neural nets to tell them what's happening at the subgrid level. So the plot on the right is showing the result of this work. So the exact solution is the blue line, and then the polynomial interpolation, which is basically the finite difference, is shown by the orange line. And then the neural net prediction is shown by the green line. So you see the neural net prediction is a lot better than the traditional polynomial interpolation. And so this is very promising. And then my idea was to like, can we actually have applications on this on cosmological simulations of galaxy formation? So if you go to the second slide. Another motivation for like bringing this up is like there are projects like the Smog Project going on here at the CCA. So you have like various individual ISM simulations, and in these very high resolution simulations, you can really simulate the propagation of the winds like to very high accuracy. And then can we actually propagate this information to use them in like cosmological simulations where you have very low resolution? So I'm not just talking about like calibrating a new velocity for the wind particles. So I'm referring to like the Springall and Hörnquist 2003 formalism, where you shoot wind particles outside the galaxy, but you're not really affecting what's happening within the galaxy at the ISM level. So it's really about substituting the right-hand side of the equations and not just changing the velocity of the wind particles. So that's what I'm thinking about, but I'm not really sure whether this can be done like in the near future. So yeah, just want to pose this challenge.
Any questions? Yes, please.
I think that's a very promising approach, but the problem here is that the resolution, right? So so you need to resolve this like parsec scales, and you need to resolve the kiloparsec scales, and then you need to resolve the megaparsec scales, and that's the hard one, right? So depending on like how many particles would you require for that resolution to happen, and what is like how many, I don't know. So that's the problem here, but I think like combining this simulation could be done, but the problem here is that only the resolution issue. So I don't know. So that's probably, but like I understand the idea that you can just write a emulator for these things, right? And then if you are able to run a high resolution simulation, you can plug your emulator there. But the problem here is that how would you run that, the large one? The biggest volume that would resolve your parsec scales as well as your like your winds or your clouds as well as your big galaxies. That's the hard one, I think.
Yeah, I was thinking you might be able to combine zoom-in simulations with cosmological ones. Like the fire simulation, you can already see like they are better resolving the propagation of the winds. And then there might be a way to combine that information into cosmological simulations. But I'm just not sure how to do that, because like in Michael's work, he's only doing like 1D hydro equation. So that's like extremely simple, but in a cosmological setting, you have all sorts of things going on.
Thank you. I think we have to move on. Next, we have Simone.
Hi, everyone. I'm going to pitch this idea of including velocities in the reconstruction of the initial conditions. This is something I've been talking with Chirag quite a bit. So first of all, let me say why we're interested in velocities. And I'm going to claim that velocities are kind of the best way to reconstruct large scales because they are not affected by shot noise. And what I mean by that is that really the velocity of a galaxy is sourced by the continuous mass distribution. You compute the potential, the gradient of the potential of the continuous mass distribution. You don't care that galaxies are discrete traces. It's really the full matter distribution that the source is velocities, and that is an important consequence. So if let's say, of course, that doesn't mean that the velocities have no noise at all. The method you measure velocities has some noise, and typically is white noise in the velocity reconstruction. So if you use continuity equation, you immediately see that the noise for density reconstruction scales as k squared, roughly. Okay, so k squared means on large scales is much lower than the reconstruction density. So if you go to the right hand figure, you see so a matter power spectrum and what's typically the shot noise for an experiment like DESI. So that's kind of your irreducible sort of noise if you use galaxy positions, your cosmological traces. However, if you measure velocities, for example, from KZ here in this case, from Simon's Observatory of CMBS4, that's the noise you get. So you see that you have a large improvement of several orders of magnitude on large scales. Okay, and so how do you measure velocities? Well, we have methods to measure velocities. You can measure the radial velocities with the kinematic Sunyaev-Zel'dovich effect. That's using the CMB that gets upscattered when CMB photons scatter in a galaxy is moving towards you, for example. You can also use supernovae. And there are ways to measure transverse velocities as well. For example, moving lens effect in the CMB. And the nice thing is we know how to predict all of this noise covariance in this, for these effects. And also, these are very much detectable in the next generation. They're already, some of them already detected. Next generation of servers will get really good measurements. So applications include local FNL, as you know, bias, large-scale bias has a large effect from FNL, but also BAO reconstruction is particularly important next to the boundary because you don't know, if you have a server with a boundary, you don't know what the matter density outside the boundary is, but the velocity knows, the velocity field knows what the matter density outside your server is, so you actually can improve BAO reconstruction quite a bit close to the boundary. And that's, since the masks are complicated and have all sorts of holes, etc., the survey footprint is a poor indicator. You actually, the boundary region is much larger in practice than you just looking at the footprint you would think of. Okay, can you go to the next slide? Yeah. Oh, okay. So this is, I think, a differentiable forward modeling simulation is kind of the natural, language for this. Includes effects of mask, the proper covariance of the signal, because of course density and velocities are sourced by the same matter field. So the idea here is you use a code that Chirag wrote, FlowPM. It's very well suited for this, and of course the particles in FlowPM already have the velocities, so it's a matter of including the observed velocities with the proper covariance in the loss function, and so you're trying to find a solution that matches both the galaxy positions and the velocities, and then so reconstruct the initial conditions, and then you can do cosmological inference from that. So of course we're going to include so realistic noise for all these kind of effects that we can measure, and we expect again large improvements on large and intermediate scales as I described previously. So I'll stop here. Thanks.
Thanks, Siema. Any questions for Simone?
Yeah, Brian. Right. So that's so Chirag can say much more about the galaxy positions only, but I think what really excited about is that if you can go to the previous slide, it's really the sort of you know. The reconstruction will be of order sort of for galaxy positions only. The order shot noise, okay, can do a little bit better than shot noise, but not much better than shot noise. So we really want to see this big improvement that kind of Fisher forecast shows on our scales, and that would be several orders of magnitude. So that's what we're really excited about.
Okay. Thanks, Emo.
Thanks.
Francois, are you there?
Yeah, I'm here. Can you go
Great.
back one slide? Yep. All right. So I'm going to be very fast because I don't want to keep you away from lunch. So my pitch here is not about a given machine learning technique or anything. It's more about tools and fundamental tools that are needed and are limiting the progress that we can make right now. So just to motivate this pitch here, I've stolen a few quotes from a bunch of papers here on the left. And if you've used machine learning for 3D data, you're very familiar with this. And the issue is that you quickly run out of memory on a single GPU. And for instance, there is this paper from Ian here that mentions that it's an issue. They're limited by the amount of space they have on a GPU. And then to process large scale data, they need to find ways to split the things in pieces. And that's a big pain. So we have a general lack of mainstream model parallelism frameworks that we can use for scaling up machine learning to the very large data sets or thing that we want to do and that we've talked about here in this conference. So I don't want to go through all of the different types of parallelism that exist, are currently supported, but the main takeaway here is that the type of parallelism that we care about is not the same type of parallelism that the industry cares about. And so we don't have a lot of tools. We have still demonstrated with Chirag last year that you can adapt some of the current frameworks that exist, this mesh TensorFlow framework here, to actually distribute your machine learning models across many different GPUs. And so the image that you have here on the right at the bottom is scaling up this FlowPM code that you've already heard about to 2,000 cube simulations distributed on 256 GPUs. So we have demonstrated that you can do that. But if you want to go to the next slide, the thing that I'm interested to talk about today with people who want to join the discussion here is where do we go from here, and can we assemble a group of people that would be interested in promoting these tools? So distributed machine learning tools for application in astrophysics and cosmology to the next level. And so, for instance, one thing that I'd like to lay the foundations for is some type of particle mesh library that would allow you to implement your n-body simulations in something like JAX to automatically allow you to distribute them on many GPUs. If you are interested in just doing machine learning at scale on large-scale 3D data, this is also something that I think we could try to push forward and try to demonstrate that you can do this in a few targeted applications. So if you're interested in scaling up your applications to large-scale GPU clusters, I'd be very much interested to talk to you about that.
Thanks a lot, Francois. Any questions for Francois? Yes.
Hi. Yeah, I'm a little bit surprised that you're using JAX here, since as far as I know, there's no public way of running multi-node JAX currently.
Yeah, exactly. So this is why I say this is very, very recent. In the last few months or so, this has become possible, and it's kind of still in development. But I think this is going to be the future, and so it's not too soon nor too late to start thinking about what kind of tools we would need and how we can build on those frameworks.
Yeah, thanks.
Thanks, Francois. Next, we have Kate.
Hi, everyone. My name is Kate. Hi, everyone. I'm Wachi. And we wanted to briefly talk about work that we've been doing with David Hogg and Soledad VR, as well as Ben Golden-Smith. So the idea, this is a paper that you can follow in archive now, is to embed equivariance in our machine learning models. And the idea for our particular model is to only use scalars of the inputs. So this means reducing any input vectors, tensors, and taking inner products, things like that, and reducing them to scalars. And that makes it so that it doesn't depend directly on like the values of whatever your inputs are, but rather these combinations that are what end up mattering more physically. Do you want to talk about the example?
Yeah, so basically for this method, we are using the scalars, right? So it makes it invariant by like just by using the scalar itself. So here you can see we have actually this is a equivariant example. So here we have like O3, so we have like 3 dimensions, and we compare our methods with the equivariant MLP methods and other like so here we have MLP and we have like the augment. The augment just means we applied like this we applied like the rotation, random rotation, and help the data to so expand the data sets. Maybe we will see better performance. As you can see here, we have better performance as, compared to MLP. But our method is like the scalar method. It's very simple. It's very elegant. We just compute the inner products of all the vectors so that they are just the scalars. So it's very simple, and you can see our performance is much better than the other methods, and it's very extremely fast because we're just using the scalars, right? And we just use like a simple neural network like linear and then the nonlinear and so on, like 3 layers, and the performance is really nice and it's really fast and very efficient.
Yeah, so Wachi's already gotten great results with this method, which the paper is mostly theoretical, so we just have a new implementation, and we'd like to apply it to cosmological problems. So I think a lot of cosmological problems could benefit from this because they have translation symmetry, rotation symmetry, things like that. So one that we're kicking around is if we can take n-body only simulations and the dark matter halos and try to predict the location and masses of the galaxies, which are the things we actually observe. And this is not quite as a clean equivariant problem as like predicting the moment of inertia, for example, but it still shouldn't depend on rotating your box or translating all your particle positions one way or another. And so we think that this model should be able to help with this problem. And if you have other ideas of problems you think would be fun to apply this method to, we would love to hear them.
Yeah, so actually, the methods we also did some other examples for the scalars. For example, we have the double pendulum thing. We can like apply the same scalars idea. For example, we use the scalars method with like using the neural network with the scalars to try to like estimate what's the Hamiltonian function is. Then after that, we can use like just like the integrate the Hamiltonian and get the results, right? But also we want to combine our methods with the neural ODE. For example, use combine the scalars with the neural ODE. Maybe we can solve some other like n-body problems and so on. So if you guys have any like kind of like interesting problems, and please let us know. Maybe we can try to see whether we can move forward with that. Thank you.
Paco?
Yeah, this is amazing. So I was wondering about the application. Are you sure that this, I mean, taking a dark matter halo and putting galaxies as a rotational invariant problem, I mean, I think we know that the tidal tensor and this thing should matter, no?
Right, so locally it might not matter, but the idea would be to take in enough information so that globally, like you should be able to rotate, your entire box, right? And you should then, if you put in that new halo position, be able to predict that new galaxy mass position. But you're right that locally it doesn't work that way. But yeah, if you have other kind of it would be easier if we could work locally because of the size. So if you have other ideas of interesting problems that would be equivariant or invariant, that would be
great. Great. Thanks a lot, Kate, Wachi. Last one. All right, next we have Hema.
Hey everyone, my name is Gemma Moran. I'm a postdoc in the Data Science Institute at Columbia, working with Dave Fly. So I'll be very brief, but I'd just like to talk about a new method called the sparse variational autoencoder. We use autoencoders to get latent representations Z. And one thing that we want to do with these representations is interpret them in some way. So one dimension, might correspond to shape, or one dimension might correspond to rotation, for example. But a problem with interpreting these representations is that VAEs are unidentifiable. So you can rotate the space and still have the same likelihood. And this means that, if we find a solution, we don't know if it's actually the correct solution. So we want to impose constraints on the VAE so that it is identifiable. Next slide, please. So we make the assumption that in our original data, there are features that depend on only one latent dimension of Z. So we call these anchor features. And we can prove that under additional assumptions, if you have these anchor features, then you can get an identifiable model. And then you can interpret the latent space based on what anchor features it's connected to. And so to do this, we impose sparsity-inducing priors on the VAE decoder to estimate the anchor features. So currently, this is more appropriate for tabular data, but we're looking to extend it to image data and other kinds of data where, we can make these similar assumptions for identifiability. So no cosmological applications as of yet, but if anyone is interested in chatting, that'd be great.
Any questions?
Yeah, is the sparsity constraint is on the weight of the decoder or on the representation that you built?
It's in the decoder. So the idea is that, in this picture on the right, so for instance, for the first dimension of X, it only depends on one of the Zs, one of the dimensions of Z. So it's in the mapping itself, not on the latent Z.
Okay, cool. Thanks.
Mm-hmm.